Okay, so we'll just head to our curriculum. Um, yeah. So as I have stated, so today we'll be discussing the regression as a type of supervised machine learning, and yeah, you will see the difference, the types of regressions, and the difference between regression and classification. Which classification is also another type of supervised machine learning. So we'll just head down here and now see the explanation of what regression is, the difference between the different types of regressions. So, regression is a supervised machine learning technique in machine learning that focuses on predicting continuous numerical outcome based on input features. So, the key thing to note here, when you're distinguishing between regression and classification is regression predicts continuous numerical outcomes, whereas classification categorizes the output based on categories. So in this case, regression predicts using continuous numerical outcomes based on input features. And we'll get to see that input features are independent variables, while outputs are dependent variables. They depend on the independent variables. So the main objective of regression is to establish a relationship between independent variables, which in this case is input features, and the dependent variable, which is output. And in this case, when you're trying to find the best fitting model of a certain type of data, the most the most thing that we will focus on is the dependent variable. So based off this variable, what will be the output? Based off the input, what will be the output? So we'll proceed here. So understand the concept of regression in machine learning. So in regression, we attempt to fit a model that best represents the relationship between dependent and independent variables. So, and later on we'll see that there is simple linear regression, multiple linear regression, but we'll explain them later on. So, in regression, we attempt to fit a model that best represents the relationship between the dependent and independent variables. This model is used to make predictions on new and seen data, as we had described supervised machine learning. Then linear regression is a common type of regression where the relationship between the variables is modeled as a straight line. So linear regression is a type of regression, which we'll also see types of regressions. So examples of regression problems include predicting house prices, estimating stock prices, or forecasting product sales. So differentiate between classification and regression tasks. So in classification, the objective is to predict a category or class label for a given input. Examples include spam detection, image recognition, and medical diagnosis. So to simplify what classification is in this case, it will categorize, let's assume an email, you've been sent an email. It will categorize that email as either spam or not spam. So that's a category. There is the spam section and there's the not spam category. So simply classification categorizes them based off, it predicts them based off categories. Whereas regression is used to predict a continuous numerical value for a given input. Examples include predicting house prices, estimating stock prices, and forecasting product sales. Regression models predict continuous outcomes. So in summary, regression is a supervised learning technique used to predict continuous numerical outcomes, while classification focus on predicting discrete categorical outcomes. I hope we have understood the difference between those predicting models, whereby we've said regression predicts continuous numerical. So sorry about that. They keep on experiencing internet issues. So as I was stating, where was I? Oh, I was explaining the difference between the two, classification and regression. So as we've seen, regression is predicting continuous numerical values, while classification is a predictive model that is based off categories. So in case this is a fruit, it gives it an apple category, a banana category, or yeah, such kind of categories. So the first form of regression, type of regression is simple linear regression. So Simple linear regression is a basic regression technique that models the relationship between a single independent variable, which in this case is the input feature, and a dependent variable, which in this case is output, as a straight line. So what you'll get to see is that they are directly proportional to each other. So the goal is to find the best fitting line that minimizes the error between the predicted and the actual values. So the equation for simple linear regression is right here. So y equals to, you can see you from your end, from the curriculum, it's stating b, but it's not b, it's beta. Like, you know, the sign of beta, it simply looks like a capital B, but with an extended bottom side. But let's just use b here for, since the curriculum is stating that. So y equals to bo plus b1 times x. So in this case, it will be y equals to beta nil plus bx1, because when you multiply this, the variable that will the new variable that will pop is bx1 when you multiply these two. So y is the independent variable, so that's the output, whereas x is the independent variable, which in this case is the input feature. Bo is the y-intercept, while b1 is the slope of the line. So b1x is the slope of the line. So the objective is to find the optimum values for BO and B1 to minimize the error between the predicted values and the actual data. So to simply explain this better, we'll just open our Google Colab, then implement this simple linear regression using scikit-learn. So you'll just head to open Google Colab, sorry. Hey. Now, after opening Google Colab, now we'll get to see how you implement simple linear regression using scikit-learn. So what I'll do here is I'll just copy this, then explain what this means. So we can see now the first thing that you note here is we are importing libraries. So in this case, we have imported NumPy as NP. Then from scikit-learn.linear model, we have imported linear regression. In this case, linear regression is the class that is used in scikit-learn that implements the linear regression algorithm. Then the next thing that we are importing is from scikit-learn.model selection, import train test split. So in this case, train test split is a function to split data into training and testing sets. So that is the purpose of importing it. So that's the function for to split data into training sets. Then from scikit-learn.metrics, import mean squared error. So this mean squared error is a function that is used to calculate the MSE, which in this case is the mean squared error, which is a common metric value for evaluating regression models. So the lower the MSE, the better the model fits to the data. So that is what we're going to know if this type of model fits this type of data. So you use MSE, and there are other functions that are used to evaluate regression models. We'll have a look at them later on. MRE, the mean squared error, yeah, we'll have a look at them. So what this does, so we have tackled that. So these are the libraries that are necessary to import. So the next thing is creating sample data. And I think we all know how to create an array of data. So there's X and Y. Then the next thing that we're going to do now is splitting the data into training and testing sets. So we have taken X train, X test, Y train, and Y test. So we have divided the data into two. So on the X sample data, we've divided it into the train data set and the test data set. And for the Y, we have given it the train data. We have split it into the train data set and the Y data set. So After giving them the variable names x train, x test, y train, y test, now you go and use the function, which in this case now is train underscore test underscore split. And in this case, we are referencing back to this data up here. This is the data we're going to split. So train underscore test underscore split, which is the built-in function, equals to x and y. Then test size, in this case, it states that 20% of the data is the one that will be used to test. And random state equals 42 is like a function that is built in to make the set more reproducible. So in this case, to randomize the selection of the data, you use random state 42. Then the next thing that we're going to do is now create a linear regression model. So model is equals to linear regression. So this is the name that you've given your model. Then run the function linear regression. So then the next thing is now to fit the model onto the training data. So you'll reference this to the linear regression model. So you give it the name model. Then now when you're trying to fit that model into the training data, use now the variable name that you gave it, then the function dot fit. So model dot fit x train and y train. Then the next thing is now to make the predictions on the testing data. Y underscore pred is equals to model dot predict for the X test data, which you can see that right here. When you're splitting the data sets into training sets and testing sets. So ypred is not ypred, but model.prediction is used to train the model to make predictions on the testing data. So in this case, on X tests. And the result for this is mainly an array of predicted target values. Then the last thing that we're going to do now is now evaluate the model. So as I had stated earlier on, the lowest MSE simply states that this is the best model that fits into this data. So if the MSE is 0.0, that states that this is the best model that fits into this data set. If it's like 7, then you use, let's assume you use this evaluation technique of MSE, then you find 7, then another one, you find like 2. 2 will be the better fitting model for this certain type of data set. So when you evaluate the model now, you'll use the MSE equals to mean squared error equals to y test and y pred. And y pred is simply the prediction of the testing data. So when we run this, let's give it some time. So you can see here that the mean square error is 0.0. So this simply states that this is the best model that fits into this data set. I think we're good till there. So that is a simple linear regression for you. And in this case, we are evaluating an input, a single input to a single output. That's why it pops as a straight line. But later on, we'll see that there is the multiple linear regression, which is our next thing. But so as you can see on the note right here, to evaluate the performance of simple linear regression models, use different metrics such as MAE, mean absolute error, mean squared error, root mean squared error, or R squared. So in this case, as we have used mean squared error, and that is the metric that we'll be using for most of the part in this course, in this section, that is the main metric that we'll be using to evaluate the regression models. You can try using MAE, RMSE. Let me give that as an assignment for you guys to try to evaluate the performance of a model using this other metrics. So RMSE, MAE, and R squared or R squared. So now the next thing is multiple linear regression. Multiple linear regression is an extension of simple linear regression models. Wait, let me repeat it. Multiple linear regression is an extension of simple linear regression that models the relationship between multiple independent variables and a dependent variable. The goal is to find the best fitting hyperplane that minimizes the error between predicted and actual value. So you'll get to see that the difference between now the simple linear regression and multiple linear regression is, in this case, there are multiple independent values. Whereby in simple linear regression, it was a single input. Let's go back here. So in this case, you can see here it's a single independent variable. So in this case, it was a single input. But on multiple linear regression, there are multiple independent variables or multiple input features. So that's the difference between the two. And now the equation for multiple linear regression is y is equals to beta nil plus beta 1 times x1 plus beta 2 times x2. So in this case, you can just simply say y is equals to beta nil plus bx1 plus bx2, so on and so forth till the last figure bxn. So in this case, y is the independent variable or output, x1, x2 till the last term x, so xn are the independent variables or input features. Then bo is the y-intercept, b1, b2 till bn are the coefficient of the independent variables. And that is what we have seen here. You're multiplying the coefficient times the independent variable. So the objective is to find the optimum values for bo, b1 till bn that minimizes the error between the predicted values and the actual data points. So now we'll see how to implement multiple linear regression using scikit-learn. And once again, to keep in mind, you are finding the relationship between multiple input features with an output feature. So that is simply multiple linear regression for you. And for simple linear regression, we have stated that you're finding the relationship between a single input feature against a single output feature. So simply in simple linear regression, we think that it's directly proportional to each other. So an increase in input features is an increase to outputs. So I'll just paste this and explain what syntax means. So far, is there any question? Just proceed. So once again, we have imported, now in this case, now we've imported NumPy as NP and Pandas as PD. And the same thing, we have imported the class linear regression for finding the linear regression algorithm, train test split for splitting the data, and MSE for as the metric for evaluating this regression model. So the first thing you can see here is we have created a sample data, and in this case, we have given it x1, x2, and y. X1, we've given this array of values, x2, we've given this array of values, and y, we have given it this array of values. Then the next thing we're going to do is now convert this data into a data frame, which we have done that using df is equals to pd.dataframe, which is the panda function of converting to a data frame. Then now x is equal to data frame x1 and x2, while y is equal to data frame y. We have furthermore specified on what the x will be. So x will be x1 and x2 in the data frame data, and y will be the specific data set or array y1, which in this case is in this data set called data. Then the next thing we're going to do is now split the data into training and testing sets, as we had seen in simple linear regression. X train, X test, Y train, Y test is equals to train underscore test split. Then we reference back to the data that we want to split into training and testing sets. So in this case, it's X and Y. Then the test size equals 0.2. And as I said, 0.2 simply means 20% of the data will be used for training and testing sets. Then random state 42 is for randomizing the selection of the data. Then now creating a linear regression model. So we had seen this. So we'll create a linear regression model where we give it the name model equals to linear regression. Now we have created a linear regression model for our data, then fit the model on the training data. So the name that you give the linear regression model is what you'll use as a prefix in the fit model function. So model.fit x train and y train. Then make predictions on the testing data. So y underscore pred is equals to model.predict. So one thing you need to know again here is you're using the prefix of the linear regression model that you used here. So model.predict. So this is the built-in function for making predictions on testing data. So model.predict, or then now we reference to making on what predictions on what test data do we want to make a prediction. So in this case is the X test. Then now we evaluate the model. So let's run this. So as you can see that now the MSE um, equals to 0.0. And as I stated, the lower the MSE or the lower the metrics, if you're using RSME, if you're using MSE, the lower that metric, the better the model the better the fitting model into the data. So if it's 0.0, it means that this model fits best into this data. So that's MS, not MSE, but multiple linear regression model. Then we'll head to the next thing, which is now polynomial regression. So simply, okay, the terms here will be a bit complex, but simply to explain polynomial regression is instead of a straight line that we have seen in multiple linear regression and simple linear regression, in this case, you'll draw a curvy line that fits the dots better. So this is mainly used in in predicting the prices of properties. So that you don't miss out so much on your data, you'll use polynomial regression. Since now in this case it uses a curvy line, and the purpose of using polynomial regression is to capture more complex relationships between the inputs and the outputs. Yeah, that is simply what polynomial regression is. So let's see what the curriculum states. So polynomial regression is a type of regression analysis where the relationship between the independent variables and the dependent variable is modeled as an nth degree polynomial. Polynomial regression can model more complex relationships than simple linear regression. As I have stated, that it is used to capture more complex relationship between your data points. So the degree of a polynomial is just a fancy way of saying how many times the variable, which in this case is x, is multiplied by itself. So if we have a polynomial degree of 2, it means that the x multiplied itself 2 times. At So when we talk about nth degree polynomial, we mean that a polynomial has a degree of n. It might look something like this. So this is quite complex, but we'll see now the equation for polynomial distribution just under this. So let's just understand the concept of polynomial regression since this is a bit complex. So this is the equation for polynomial regression. So y equals to beta nil plus beta 1 times x, beta 2, bx2 to the power of 2 plus. So the data set is quite long. Then the last figure will be bn times x power n. So y is the dependent variable. In this case, it's the output. X is the independent variable. In this case, is the input. BO is the constant term. B1, B2 till Bn are the coefficient of the independent variable powers. So as we have stated again here, that let's reference back here, that the degree of a polynomial is just a fancy way of saying how many times the variable is. So if we have a polynomial degree of 2, that means that x multiplied itself 2 times. Now we'll reference back to it when we write down the syntax. So let's just copy this. Let me explain what this is. So in this case, we've imported the libraries and we have stated all these first one. So the new one now for finding the polynomial features is now the polynomial feature library. So from scikit-learn.preprocessing, import polynomial features. So the first thing that we're going to do is now create a sample data, and we're going to give it two variables here, x and y. Then later on convert them into a data frame. Then we define a new variable, which in this case is x, is the data frame x, and y equals to the array y in the data frame data. So then the next thing is splitting the data into training and testing sets. So x train, x test, y train, y test equals to train test split, then xy test split is equals to 0.2. Once again, I think we have already discussed all this, but test sizes simply indicates that 20% of the data is going to be used as a training and testing set. Then random state 42 is used for randomizing the selection of the data sets. Then now the new thing here you're going to see is now creating polynomial features objects with the desired degree. So you're going to give now a new variable name poly features, which later on you're going to reference it when you're transforming the input features to polynomial features. So you'll create some new variable name called poly features, or to your liking the variable name that you'll use, then equals to polynomial features degree 2. So this is our desired degree. Then when we drop down, now we're going to transform the input features to polynomial features. So the purpose of converting the input features to polynomial features is now to use the polynomial regression method. So x train poly. So this is your this is your the variable name for your trained data. So x train poly equals to poly underscore features. So I had stated here, the purpose of creating polynomial features is when you're transforming the input features to polynomial features, you'll reference back to the object or the variable name here. So x train poly equals to poly underscore features dot fit transform. So in this case now, this is the built-in function for transforming the input features to polynomial features. And now we're going to reference back to which data set we want to transform to polynomial features. So in this case, we want to transform the x train. Then x test poly equals to poly underscore features dot or Benedict, random state, is the random state 42 the standard, or it can change? It can change. It is to your liking, but mostly we use 42 since that is the best reproducible figure that mainly we use. So even when you go and browse, you'll see that random state 42 is the not default. I don't want to call it default, but is the preferred value since it is mainly used for reproductive data. Have I answered your question the right way? But mostly you'll just be finding yourself inputting random state 42. That will it's I don't want to call it default, but that will be your default. Most of the time, as a data scientist, when you are splitting the data set, you'll be mainly putting random state 42 as the default value for the random state. Have I answered your question? Okay, I think I'll proceed. So now on the test data. So now on the test, please send the GitHub link. Okay, let me copy it. Paste the GitHub link on what we're discussing today. So okay. So let's head back to our Google Lab. So after creating the objects, the polynomial features objects, we're going to transform now the input features to polynomial features. So in this case, x train poly is equals to poly underscore features dot fit transform. So what you need to keep in mind here is the function for transforming the input features to polynomial features. So in this case, dot fit underscore transform is the function that you need to keep in mind when you're transforming this training data set. So in this case, x train data set. And when you are transforming the input features to the polynomial features for a test data set, it's now dot transform. So x underscore test underscore poly equals to poly underscore features dot transform now for the x test data set. So we subdivided them right here when we are splitting the data. So now we'll create a linear regression model, and we've already discussed on the purpose of doing that. So model equals to linear regression, and now fit the model to onto the transformed training data. So model dot fit. Now this polynomial features that we transformed right here is what you're going to reference here when you're trying to fit the model. So X train poly and X test poly, but you can use Y train. I don't know why we're using Y train here, but you can choose either of these two. Then now make the predictions on the transformed testing dataset. Oh, sorry. You cannot use the test dataset on this since this is fitting the model onto the training dataset. And now making predictions onto the testing dataset now is where you're referencing back to X underscore test underscore poly. So you'll use this testing dataset for making predictions and the training dataset for fitting the model onto the trained data. So make now the predictions on the transformed dataset. So y underscore pred equals to model dot predict. Now this transformed input feature or the polynomial feature. So y underscore pred equals to model dot predict. So what you need to keep in mind is when you're making predictions of a transformed data set, you use dot predict, then reference back to the test data set. So if you're using a linear regression model, you reference it to it as the linear regression model. So, and in this case, we're using polynomial. So you're referencing back to the polynomial feature, which you created here, where you're transforming the input. So y underscore pred equals to model dot predict, then reference back to the polynomial dataset, x test poly. And now evaluate the model. So you're going to evaluate the model based off the MSE metric. So MSE is equals to mean squared error of the y test and y pred. So when we run this, can see the MSC, the mean squared error is 0.0. And once again, as I had stated, that the lower the evaluating metric, the better the model for the certain data set. So in this case, we're using the metric, evaluation metric, mean squared error. So if you're using RSME, then find 0.0. That simply means that that specific model fits best into that data set. So the lower the figure that you get on your evaluating metric, the better the model onto the data. So we'll head to the next type of regression model, which in this case is now, oh, before we head to the next one, we'll just have a look at regularization techniques. But under this regularization techniques, we'll find that lasso regression is another type of regression technique in supervised machine learning regression. So regularization techniques are used in regression models to prevent overfitting, improve generalization, and balance model complexity. So we'll see what overfitting and underfitting is. So overfitting is when a model performs well on the training data, but poorly on the testing data. It is said to be overfitting. So the condition to describe that certain model is overfitting is when the training data performs well and the testing data performs poorly. So this occurs when the model captures noise in the data, when it is fitting it too closely, and thus fails to generalize well to new data. So that is simply overfitting. What you need to keep in mind is when a model performs well on training data and performs poorly on testing data, that is overfitting. And how does overfitting happen? It is when the model finds noise in the data or it fits the data too closely. Then underfitting is when a model performs poorly on both the training and testing data, it is said to be underfitting. I remember when we were introducing machine learning, I asked you guys which, if you were to run into an error, which error would you prefer? And basically, it's I think everybody's answer will be overfitting, since underfitting is two bad things. It has performed poorly on the training dataset and the testing dataset. Whereas overfitting, it has performed only on one side, either the training or the testing data. So this occurs when the model fails to capture the underlying patterns in the data, often due to excessive simplicity. So this simply means that the model is not really not, I don't want to call it intelligent, but yeah, let me just say it's not really intelligent. So the regularization techniques for these two errors right here is ridge regression and lasso regression. So ridge regression is a technique that adds an L2 penalty to the linear regression objective function. This penalty term is the sum of the squared coefficient multiplied by the regularization parameter. So in this case, it's the alpha. Then ridge regression prevents help overfitting by shrinking the coefficients, thereby reducing model complexity. So that is the first way of regularizing the overfitting and underfitting issue. Then the other one is the lasso regression, which in this case is the L1. So lasso regression is another regularization technique that adds the L1 penalty term to the linear regression objective function. The L1 penalty is the sum of absolute values of the coefficient multiplied by the regularization parameter. So for L1, it's the absolute values of the coefficient, whereas in L2, it's the squared coefficient. It's the sum of the squared coefficient, whereas in this case is the sum of the absolute values. So you'll add the values independently, then multiply them by the regularization parameter. Whereas in L2, you'll find the sum of the squared coefficients, then multiply them by the regularization parameter. So in this case, it's alpha. So lasso regression not only helps prevent overfitting, but can also induce sparsity in the model. So as we had seen here, if you fit a data set in too closely, you experience overfitting. Whereas in lasso, it induces sparsity in the model. So it simply terminates overfitting using inducing sparsity in the model, setting some coefficients to 0 and effectively performing feature selection. So let's copy this data then explain what it means. Well, now, the first thing that we will see here is the new thing that we're importing now from the linear models is ridge and lasso. So you don't have to import them individually since we want to use both methods. So that's the new thing, I guess, here. So once again, we discussed on this function that we're importing that is used to split the data, then MS is used as the evaluation metric of the model. So in this case, we have created the sample data, then given them these values, x1, x2, and y, then converted this whole data into a data frame using pandas. Then we later on dictated that on X, we want it to be the data frames X1 and X2, while Y, we want it to be data frame Y. Then once again, we'll split the data into training and testing sets. So X train, X test, Y train, Y test is equals to train underscore test underscore split. So this is the function for splitting the training and testing sets. So we are referencing back to this data right here. So we want to split this data into training and testing sets. So we reference back to it. So X, Y. Then the test size is 0.2. Once again, 0.2 means 20% of the data will be used for training. Then random state, 42. Then now we're going to create ridge and lasso regression models. So ridge equals to ridge. So ridge is the function. This is just the name that you're going to give it. So ridge equals to ridge alpha, alpha is equals to 1. So what this does is it creates an alpha, it creates a ridge expression model with a regularization strength of 1. So what the alpha means is that it is a regularization strength. And we had seen that we're going to multiply the some in lassos, we're going to multiply the absolute values multiplied by this alpha value right here. While in ridge, we are going to sum up the absolute values, then multiply them by the regression strength, which in this case is alpha 1. So simply, you need to keep in mind that alpha 1, ridge alpha 1 is used to create a ridge regression model with the regression strength of 1. So alpha is equals 1 is the regression strength. So ridge regressions adds a penalty equal to the sum of the squared if coefficients to the loss function in ridge. Whereas in lasso, it creates a lasso regression model with a regularization strength of 1, whereby it adds a penalty equals to the sum of the absolute value of the coefficient to the loss function. So in this case, it adds a penalty equal to the sum of the squared coefficients. And in this case, the coefficients are beta nil, beta 1, so on and so forth till beta n. So those are the coefficients. So it adds a penalty into the sum of those coefficients when they are squared. But in lasso, it adds a penalty equals to the sum of the values of the coefficients. So it will add beta nil, beta 1, beta 2, beta 2, beta 3. Then it will add a penalty on that sum of those coefficients. I think we are clear till there. Then now, since we're using this regression model, so we'll give it a new variable name for the fitting the models into the training data set. So ridge.fit. So you're referencing back to these regression models. Since you give them the variable name, ridge, and this one you gave them, you gave it lasso. So you are going to, when you're fitting the models, you're going to reference back to those regression models. So ridge.fit, X train and Y train. Then lasso.fit, X train and Y train. I think we have already seen this. The syntax is simply the same in fitting the models in all the data. The only thing that you are doing is converting the given values into data frames, then into the regression model that you're using. So in this case, this is converting into the regression model that we're using. Then now fit the models onto the training data, and now make the predictions on the test data. So y underscore pred underscore ridge is the name that we've chosen, equals to ridge.predict on the x test data set. Then y underscore predict using the lasso equals to lasso.predict for the x test data set. Then MSE ridge and MSE lasso. So we're going to find the mean squared errors of both methods, the ridge and the lasso. So MSE ridge equals to mean squared error of the y test and the y pred ridge. So y test is the y test data and the predicted test data. Then when we find the mean squared error of the lasso data set, or using the lasso method, is MSE underscore lasso is equals to mean squared error of the y test and the y predicted lasso data set. So let's run this. So we'll see that the mean squared error for the ridge is 0.018 and the mean squared for the lasso is 0.3265. I think we're good till there. Is there any question so far? So, and let me explain. So the purpose of this specific syntax right here is it is used to simply demonstrate how you use the ridge and lasso regression methods, which in this case we are using them as regularization techniques for the overfitting and the underfitting in linear regression models. So the next thing we're going to discuss is SVR, which is simply derived from SVM. I think we had discussed on SVM. So support vector regression is an extension of SVM, support vector machines, for solving regression models. The goal of SVR is to find a function that best approximates the relationship between input features and output values while considering a margin of tolerance. So the thing that you need to find here is that SVR is used to find a function, and the other thing that you need to do is it does that while considering a margin of tolerance. So let's understand now the concept of SVM for regression. So in SVR, the objective is to fit a hyperplane that has a maximum margin while allowing some tolerance for the error in the predicted values. The margin of tolerance is determined by the parameter called epsilon. So what you'll get to see here is that when you have added the coefficients, y is equals to beta nil plus beta 1 multiplied by x, at the end of each coefficient, you'll see that you'll be adding this parameter called epsilon. It is noted by the like an E-looking character. So SVR tries to minimize the error within this margin while also minimizing the model's complexity by penalizing large coefficients. I think you'll have to bear with me since I'm experiencing these issues, these internet issues once in a while. So I think the last thing we were talking is now understanding how SVM is used for regression. Not SVM, but SVR. Can you please confirm if we have stated the margin tolerance that is noted by the character epsilon? Had we discussed still there? So that I don't want to skip any section. Can you please confirm the maybe the last section that you guys had? Okay, well, I'll just proceed from there. I'll uh, I'll assume that was the can. Oh, sorry, I had not seen your questions. Can the MSE be in the negative, say 0 point negative 0? Not really, since that will indicate like okay, the chances of that are I've never ran into such a value when I was trying to fit a model, but no, I'll say no, because that will simply mean that the least value that you can find is 0 0.0. When we say like when we say 0 0.0, we mean that that is the best fitting model. So that is the best value that you can find in a training when you're trying to find the best model for a certain data set, 0 0.0 is the best value that indicates that this model is the best for this data set. So have I answered your question, Benedict? It is impossible to find negative 0 0.2 since 0 0.0 is the best value that you can get when trying to determine the best model of a certain data set. I think I have answered your question. And sorry, I had not seen it. My chat is not popping quite frequently. I think I'll. Can you guys hear me? Can anybody confirm maybe with a thumbs up? Because I'm not really sure if you guys can hear me. Umza is the only one hearing me. Can either maybe Natasha or Canelo or Benedict confirm if you guys can hear me? Okay, I think you've confirmed, so I'll proceed. So there are different types of SVR, such as linear, polynomial, and radial basis function. And this is what we use right now. So the choice of kernel and its parameters can significantly impact the model's performance. So we're going to implement SVR using scikit-learn and see how it is used to define the model. So we'll just copy this, then head to Google Colab, add a new line. So now let me explain what this means. So the thing that we have done, the new thing that we can see here is that we have imported S SVR from SVM. So this simply means that it will implement the SVR or the support vector regression, which is used for the regression task in this case. So we are going to use SVR for the regression as a regression method in this case. So that's why we have imported SVR. Then I think the rest we have discussed about them. So we're going to create a sample data, convert into a data frame. Then split the data into different training data sets. So I think we have already discussed all this syntax. So the new thing that you're going to see here now is creating a SVR model. In this case, we're going to use an RBF kernel. So what this means is now we're going to give it a new name. We're going to give our SVR model a new name. So SVR is equals to, now this is the built-in function of creating an SVR model. So SVR is equals to SVR kernel is equals to RBF. So this simply states that we are using this kernel. And as we had seen here, there are different kernels like the linear, polynomial. Right here, we had discussed that. We had seen here that the different types of SVR are linear, polynomial, and RBF. So when we come here and state that we want the kernel to be RBF, we want the radial basis function to be the kernel to be used in this SVR model. Then C equals to 1.0 is the regularization parameter that is simply used to control the trade-off between achieving the lower training error or LTE and a low testing error. Then epsilon is equals to 0.1 is simply the epsilon tube, which in this case is no penalty associated to the prediction models. But you'll get the hang of it of using this regularization parameter, which is noted by C equals to 1.0, and the epsilon, which in this case is the epsilon tube that within which no penalty is associated with the prediction errors. So now we're going to fit the model onto the training data. And the function is, after creating the SVR model, you'll reference back to it. So we are going to fit this specific model into this training data set. So SVR.fit then X-train on the Y-train data set. Then now the final thing we're going to do is now make the predictions on the testing data set. So Y underscore pred is equals to SVR.predict of the X test data set. So I think this is quite clear on what we've done there. And in case you have a question, I'll keep on popping my chat pad frequently since I've seen I'm missing some of your questions. But in case you have a question, just write it in the chat pad. When I see it, I'll just explain it. So the first thing we have done here is created an SVR model. And in this case, we have specified the kernel that we want to use, the RBF kernel. Then we have specified the epsilon to be 0.1 and the regularization parameter, which is simply noted by the C character, to be 1.0. And once again, the regularization parameter, it is used to control the trade-off between achieving the lower training error and the lower testing error. So when we run this, the mean squared error is 50.4444. So this means that this is not the best regression model for training of, is not the best regression model for this data. So this model does not fit into this data. So when you have a look at these other models, you'll see 0.3, 0.01, 0.0. So you can see that the polynomial regression method is one of the best in this data set, and the linear multiple linear regression and the linear regression are also one of the best models used for this data. So you can see that SVR is not really the best. So yeah, that is the whole purpose of using this metric, the MSE or RMSE. So we'll head to the next thing. So in this case, we're going to discuss the decision tree regression. So decision tree regression is a type of regression model that uses a tree-like structure to represent the relationship between input features and output values. It recursively splits the data into subsets based on the input features aiming to minimize the variance of the output values in each data set. So the best way to think of this model, this type of regression model is you are asking a series of like yes or no questions to make a decision. That is simply this regression. That is the simple explanation of what this regression model is. You're asking yes or no, yes or no, yes or no, and it ends up to be a series of yes, no's, which in this case will come up as a tree. And that's why it's called decision tree regression method. And the purpose of using this regression model is to split the data into branches based on things like features and now make a prediction on each branch. So a use case for this regression method is like when you're trying to predict if it's going to rain today based off questions like let's say so is it cloudy? So we expect when it's raining, we expect it to be cloudy. So you're going to ask it based off this branch, which is it cloudy? So it will give you an answer, yes or no. Or maybe another branch will be, is it windy? Because most of the time rain is associated with wind. So you'll use the decision tree regression method to predict data based off those questions that you're giving it. So once again, the decision tree regression is just simply asking a series of yes or no questions to make a decision. So this is quite a tough explanation. So we'll just paste this and explain what it means. Paste this. Now let's explain what this does. So now the thing that we're going to import now, the new regression method now that we're going to import is decision tree regressor, since that is the regression method that we're going to use. So we're going to give it a sample data. So in this case, X and Y, then convert them into a data frame, then split them into training and testing data sets. Then now when you are creating a decision tree model, you'll see now the function for creating a decision tree regression model is decision tree regressor. That is the built-in function for creating a DTR model. So now the new thing that you're going to see here is now the max depth is equal to 3 and random state 42. So what max depth what max underscore depth equals 3 means, it simply specifies the maximum depth of the tree. So it will make the model less complex. So this is simply used to control the depth of the tree, which makes the model when you use a higher maximum depth, the model will be quite complex, and this will bring up issues like overfitting and underfitting. So you'll choose a shallower depth, or this is the maximum depth that we want to go, a maximum depth of 3. So it will prevent overfitting. Then random state 42, once again, it ensures that there is reproductivity of the results. So this is the seed that we have settled. Then now we're going to fit the model onto the training data. So after creating the decision tree model, we'll now come here and reference back to it when you're trying to fit the model into the training data. So d3.fit x train, y train, then now make the predictions on the testing data. Once again, this is something that we've already seen. So the main difference that you'll get to see here is now when you're creating the model based off the method that you've chosen. That is the new thing that you'll see. So making predictions on the testing dataset y underscore pred is equals to d3 dot predict. Then we reference the testing dataset. In this case, it's the x test. Now we find the MSE. So let's run it. So you can see the mean squared error is 9.0. So it's not really better than the linear squared, not the linear squared, but the linear regression model. So yeah, so we'll see that the mean squared error in this case is 9.0. That means it's not really the best model that fits with this predicting the models in this data set. So now the next thing is random forest regression. So random forest regression is an ensemble learning method that combines multiple decision trees to improve the model's performance and generalization. Give me a minute, I switch my internet so that we don't experience an issue. Yeah, I've renewed my internet since it was expiring. So, as I was stating now, random forest regression is another method that we are going to discuss. So, RFR or random forest regression is an ensemble learning method that combines multiple decision trees to improve the model's performance and generalization. Each decision tree in the ensemble is built using random subset of features and data points, which helps reduce the correlation between the trees and increase the model's robustness. So the better way of explaining what random forest regression is, like now in this case, you are asking many decision trees for their opinion and then averaging their answers. So we can see that here, each decision tree in the ensemble is built for using random subset of features and data points. So once again, I've stated that in this case, you're going to ask many decision trees for their opinion, then find the average of the answer and use it. So the main reason of using random forest regression method is mainly to combine like the predictions of multiple decision trees and get the most accurate answer based off the answers that the decision trees will give you. So, and in this case, maybe you can see like let's look for a good analogy. Um, uh-huh. So let's use like a movie rating thing. So when you're predicting movie rating, you find the average opinion of like many users. So you'll rate it a poster based off like maybe critiques from this number of users. So that's when you're using random forest regression in such a scenario where you're finding the average opinion of people on maybe a certain movie and give it the rating based off those opinions of those people. I think that's the best way to explain it. So we're going to copy this, then explain it. Okay. So once again, it's a repetition of things, but now the thing that we're going to report now is the random forest regressor, as we're going to use the random forest regressor method. Once again, it's a repetitiveness of what we've been discussing for the last couple of slides. So I'll just start from here, creating a random forest regression method. So you'll give your random forest regression model the name are forests. Then the function for creating a random forest regression model is random forest regressor. Then we specify on n estimators equals to 100. So what this simply does is it specifies the number of decision trees to be in this random forest regression model. So n estimators, as once again, it is used to specify the number of decision trees that are in the this model. And you'll come to realize that the more number of trees that are in the model, the better the model. but it can also maybe improve increase some cost like computational things. There are a couple number of trees, but the more the trees, the better the model's performance. Then once again, max depth, we're going to give it three. So the maximum depth of each tree will be three, and this controls the complexity. Let's assume you use a higher max depth here, then use extra number of trees here. The computational cost will be like out of this world. It will skyrocket since it will compute a lot of trees. It will go from to this tree, then from this tree it will divide it into branches. You see, the computational cost will be quite high. Then fit the model onto the training data set, then make predictions based off the data set. So what I'll be explaining now is like creating the regression model. So we've seen how to create a random forest regression method. So let's run this and see if this regression model fits this data set. So the mean squared error is 0.008. I think this is the second best past multiple linear regression models and linear regression models, since both of them are 0.0 flat. So I think we're good till there. So now we are going to see now the evaluation metrics, and maybe for our assignment today, since you've already discussed on the metric mean squared error, I'll give you maybe like a mean absolute error or like an RMSE for you to use that as an evaluation metric. So mean absolute error measures the absolute difference between the predicted values and the actual values. It is a simple, intuitive metric that gives an idea of the average magnitude of the errors. And once again, you'll come to realize that when you are using the mean absolute error or the RSME, you'll have to import it. So the formula is MAE is equals to 1 underscore n times this y true. This is quite complex. This is not really relevant. So just ignore that. So what you need to keep in mind is how MAE is used to as an evaluation metric in a model. So it measures the absolute average absolute difference between the predicted values and the actual values. And I'll summarize something that states this is the type of evaluation metric you use when you find yourself in this position. This is the type of evaluation metric you use when you find yourself in this position. Yeah, I'll simply give you a draft of the right evaluation metric in certain positions. So MSE measures the average squared difference between the predicted values and the actual values. So that's the average of the square difference, whereas MAE is the average of the absolute difference. Then RMSE is simply the square root of MSE. So it's the square root of the average squared difference between the predicted values and the actual values. R squared, also known as the coefficient of determination, measures the proportion of variance in the dependent variable that is predictable from the independent variables. But most of the time, you use this. Then the adjusted R squared is a modified version of R that takes into account the number of independent variables in the model. It is used when comparing models with different number of features as it penalizes model. Okay, don't worry about this. I'll just give you a draft of when to use this, when to use the other metric method, when to use this other metric method. So yeah, now let's copy this when we implementing our random forest regression method. But we've already done it, but let's just get it. So in this case, it's using different evaluating metrics. So it has used the MAE. So let's head back to our curriculum. We've stated it right here. Right here. We have stated it right here, where it's the average of the absolute. Then we'll also use the MSE there, then the RMSE and the R squared, which is noted by R2. So when we are finding when we are going to, so in this case we're going to see if we use this evaluation metric, this will be the value. If we use this other evaluation metric, this will be the value. So let's run this. So when you're using MAE, mean absolute error, use the function mean absolute error. When you're using the mean squared error, which we've been using the whole today's session, you specify mean squared error. And when you're using RMSE, since you have said it's the square root of MSE, you'll just use numpy in this case. So RMSE is equals to NP dot square root of MSE. Then R2, you'll use the function R2 underscore score. So this is the R squared method evaluating metric. So R2 underscore score, then specify the data set that you want to predict. Let's run this. Again, it had wow. Had I explained I don't like how I'm experiencing this internet issues. So I keep on repeating the same thing. Okay, had I explained this evaluation metric methods? Someone please confirm with me. Okay, I'll assume that I had explained that. So now we are going to now implement random forest regression using different evaluation metrics. So in this case, we had copied this, then we went to our Google Colab page, then ran them. So once again, let me explain what this syntax means. MAE is equals to mean underscore absolute underscore error. So this is the evaluation metric for mean absolute error. So that's the function of using the metric. Then for MSE is mean underscore squared underscore error, which we have tackled a couple of times so far. Then RMSE is simply the square root of MSE. So we're going to use numpy to find the square root of MSE. Then R2 or R squared is noted by R2 underscore score. So these are the four evaluating metrics that we'll use for our random forest linear regression model. So we can see right here that MAE gives us 0.089999. Mean squared errors give us a 0.080999. RMSE 0.089999. Then R squares gives us not a number. Why is that? R24 is not well defined. Okay, but most of the people don't use this. So let's just leave it at that. But we don't mainly use this as an evaluating metrics. Most of the time, you'll find people using MSE since it's the most common evaluation metric. So I think we're done. So model selection and hyperparameter tuning. So model selection and hyperparameter tuning are essential steps in building effective machine learning models. These processes help ensure that the chosen model generalizes well to new data points and perform optimally. Split datasets into training, validation, and testing sets. So once again, we've seen how we do that. Then uh, to evaluate a model's performance and tune hyperparameters, it's crucial to split the dataset into separate sets, training, validation, and testing. So validation is the only set that we've not done here. Then the training set is used to fit the model. As we had seen, you fit the training set into the model. Let's reference back here. You'll see right here. The training set right here is used to fit in the model. So when you think of training set, think of fitting the model. Then the testing set is used now to make the predictions of the data. So understand the concept of cross validation. So cross validation is a technique used to assess the performance of a model by training and evaluating it on different subsets of the data. The most common form of cross validation is k-fold cross validation, which we had discussed on when we were discussing machine learning, the introduction to machine learning, where the data is divided into k equal sized folds. The model is trained on K1 folds and evaluated on the remaining folds. This process is repeated K number of times. So K is the undefined variable, with each fold used as the validation set once. The average performance across all iterations is used as the model's performance estimate. So it will find the iterations on all k equal sized folds, and that is the final thing that will be used to find the model's performance estimate. So grid search and randomized search for hyperparameter tuning. So there are two methods. These are two methods of hyperparameter tuning, whereby grid search is an exhaustive search of a specified range of hyperparameter values. So in this case, when we were discussing on random forest, we've seen that we are specifying on the number of forest and the max depth of the forest of the tree. So most of the time we've seen that we've used the max depth of 3. Then on the number of forest, we've specified like 100. So in this case, grid search is an exhaustive search of a specified range of hyperparameter value. So a specified range in this case is the one I've explained, where we specified that we want the number of trees to be 100 and the max depth of a certain tree to be 3. So the model is trained and evaluated for each combination of hyperparameter values, and the combination that yields the best performance is chosen. So randomized search, a more efficient alternative to grid search. This is the more efficient alternative to grid search. Instead of trying every possible combination, a fixed number of random combinations of parameters are sampled. This approach can be faster and yield similar results compared to grid search, especially when dealing with a large number of hyperparameters. So now we're going to implement the model selection and hyperparameters using scikit-learn. I'm going to explain this. So what you're going to see now here is we have imported load Boston. So load Boston is a housing data set that is mainly used for regression tasks. So it's an inbuilt type of data set in the scikit-learn. So these are inbuilt data set in scikit-learn that is used for regression tasks. Then in this case, we have seen the train test split. Now we're going to see now the new thing, which is grid search CV. And in this case, this performs an exhaustive search over specified parameters. That one we have explained already for a model. Then using cross validations to evaluate the performance of this certain model. So I think that's what we need to know. So when we load this data is equal to load Boston. So it will load the inbuilt data set for that is inbuilt in scikit-learn for regression. Then X, we want it to be data.data. Then Y, we want it to be data.target. So one thing you need to know here is X, we have specified that we want it to be the data section. Then Y, we want it to be the target. So split the data into training and testing sets. So in this case, we'll divide them into these 4 sections: the X train, X test, Y train, Y test. Then now we're going to define the hyperparameter grid. So in this case now the paran grid. So this is this is just the name that you're going to give it, equals to the number of estimators we want them to be this. So the number of trees in the forest, we want them to be 10, 50, 100. So we're giving it a range of those of those number of trees. Then max depth, we want it to be the first value to be none, then 10, then 20, then 30. Then the mean sample split. So this is the minimum number of samples required to split an internal node. So the minimum number of splits. So the minimum number of splits to be 2, 5, and 10. Now we're going to create a random forest regressor. So R forest is equal to random forest regressor, then give it a random state of 42. Then the next thing that we're going to do is now instantiate the green search with cross validation. So grid search equals to grid search CV equals to, then define these parameters. So estimator is equals to R forest, then the param grid is equals to param grid, then the CV equals to 5, then scoring equals to neg underscore mean underscore squared error. So let me explain this. So this is the model of the tune. This R forest estimator is equals to R forest. Then param grid equals to param grid is the grid hyperparameters that is going to be used to search. So param grid underscore param grid is the grid of the hyperparameters. Then CV4, these are the number of cross valid folds. So we have specified that we want to instantiate this grid search with this number of cross validation folds. So in this case, we have specified we want them to be 5. Then scoring equals to neg underscore mean squared error. This is the scoring metrics that is used to evaluate the performance of this model. So negative mean squared error is used because grid search CV maximizes the score. So now we're going to feed the grid search into the data. So grid search, grid underscore search dot feed X train, Y train. Then now we're going to print the best combination of the parameters of the score. Boston housing predators becomes nothing. Okay, I think we are experiencing issues from this, so we'll just use a different data set. Let's just change it. So now data that, then I think again. Hopefully this time it runs. I've seen that the Boston housing data set has an issue. Taking some time before it reads the data. So these are the kind of things that we were discussing about computational cost. So if you use a huge number of trees, it will take some time. So in case we had specified the number of depth to be even bigger than the value that we stated, it will take us a lot of time and a lot of computation cost if you're doing it at scale. Taking some time. To the next day. I'm going to use this grid search method as per now. Since we have seen it's taking quite some time, but let's give it some few minutes and see what it is. Oh, so while it's running, I wanted to make a request to you guys. If you are comfortable with having a session tomorrow, I know it's not our usual day of session, but I want us to complete this course tomorrow so that now we start our project starting from Monday. So I want to start a new cohort on Monday. So I was asking if it's okay if we add a session tomorrow. Tomorrow's session will be quite long. So I was requesting maybe since it's the last session, maybe we start early, then maybe finish a bit late so that we can finish up on everything. Then have an end-to-end machine learning project. We have a deep dive into NLPs, then natural language processors. We'll have a look at transformers. I don't know if it's okay with you guys. I, Yeah, Canelo has confirmed it's okay. Okay, what I think I'll do so that you guys don't feel oppressed. So I'll just put a poll in the group chat. Then maybe you choose. Okay, CG has confirmed that you're okay. Maybe Omza has confirmed it's okay. So Canelo has confirmed it's okay. CG has confirmed it's okay. Omza has confirmed it's okay. Benedict, we only have one session left. Okay, tomorrow's session will be quite at scale. So we'll have a look at everything. Then I'll give you guys now the project that you guys are supposed to do. So tomorrow's session will be quite huge since we have a couple of things that we are to discuss on neural networks, NLPs, deep learning. That's why I was requesting maybe if we start our session early, that we have a skin in the game for quite long. Is that okay with you guys? So CG has confirmed it's okay. Omza is okay. Benedict, I don't know if it's okay with you. Benedict, Canelo has confirmed it's okay. Natasha, can you please give us maybe your view on it, if you're okay with it? And I'm talking about 4:30 East African time. I think there was a miscommunication last time with Natasha where she thought 5:30 was in. I don't know if you use GMT, but yeah. So let's see if our data set is. It, oh, it's taking some time. And those are the flows I was talking about when you specify a huge parameters. Okay, I think it is consuming most of our time. So what I want you people to do, maybe from your end, let it run. So it will give you the best combinations that you can use in the models. So the output will be in form of it will just give you the best combinations of the models that you can use. But on today's session, I'll just send a slight summary. Then tomorrow on classification, so easy since we have already discussed on regression. Classification will be so easy since classification is categories, and this on regression it was specified, but on classification it's categories, so it's on a broader view or on a broader scale. I think it's and another maybe another thing is I have bad internet, so maybe you can try it from your end, then tell me what will be the output. So I'll give you guys a simple task today, a simple assignment, then you'll submit it directly to my DMs. So yeah, I'll give you a data set. Yeah, we'll proceed from there. So is there any question? Well, if there is no question, I think we're gonna join today's class. Then meet tomorrow. I'll set the class to be 4:30. We have solid time so that you guys can go back to your normal businesses and your normal activities. Because for some of you, I think it's interfering with your normal operating times. Because I think for people in like Botswana, it's like 4:30 when in Kenya it's 5:30. So that's quite early. And for people like maybe Natasha who's in Sierra Leone, it's quite early. It's like 2:30. So that's the reason I want tomorrow's class to start early so that we can finish up on everything. Then now we start on the project. So a project will be easy since you'll just be it will be like a one-on-one type of a session where you ask me what you want, not what you want, but I'll give you the guidelines. Then you when you have a problem, you just handle me, not handle me, but DM me. Then we handle the issue together. So Benedict says I'll have a packed for lots of meetings. I don't know if it's okay with Benedict. I don't know if it's okay if we record the session, then maybe you have a look at it later on. Okay. Since you've confirmed, so tomorrow's class, I'll set it early, so 4:30 Kenyan, East African time. So let's meet tomorrow. You guys have a fantastic evening. Yeah, Benedict, we have one session. So tomorrow will be quite huge. That's the reason I'm starting the session early so that you guys can ask all the questions that you require. I'll give you the good steps on how to handle these kinds of things. Tomorrow will be quite it will be quite huge. That's why we are going to scope it from 2 hours to 3 hours, to upscale it from 2 hours to 3 hours tomorrow. So yeah, we have one session left. So if there is no other question, you guys have a fantastic evening. Let's meet tomorrow.